Okay, we're recording now. That's homework 4. How about homework 5? I think it makes sense while you're doing homework 3, especially that visualization part, to look at homework 5 to ask what it does. You don't have to do homework 5 now, but it can help to look around, right? So you're gonna have to have that graphical interface with a little modification to allow you to be a judge. So you're gonna see there the query. The queries you already have are the ones that are marked with a number in Dropbox. So if you see there things like 150201, recent popes. That's not the right number, but that's not the URL in your Dropbox. It's like a subtopic or so. You can use this one as a query, and I can give you more queries. But the important part for homework 5 is that you're going to have to go through so many documents and mark them 0, 1, 2. We're going to start talking about these annotations today, and we're going to finish on Wednesday. But you're going to have to pull those documents, not just display them like in homework 3, but have some sort of indicator function ability to mark them 0, 1, or 2. In the past, we had students who said, I'm a terrible programmer in JavaScript, so I don't know how to do that. Can I literally look at the document and create an Excel sheet by hand when I type the URL of the document, my name, the user judge, so we know, because in your teammate there will be 3 people, right, that do this. We need to know the annotation comes from where. And the annotation, so we have 3 columns Excel sheet. And we allow that, since the purpose is not necessarily JavaScript. So if you really don't want to change the interface from homework 3 by adding this annotation mark ability, or you can do stars or whatever input that serves as 1, 0, 1, or 2. We said, okay, you can manually create a CSV or Excel or table format where you copy paste the URL of the document, you put your name in there, and then you have a mark 0, 1, or 2. I think it's relatively easy to create just a web interface to do so, and you only need 1 per team. So if anybody in a team creates such an interface, all 3 members can use it, but you need to submit the result files in some tabular format. URL, judge, and the annotation, and if you have 3 judges, I'm not sure, there might be in here a format. That's the format that is specifying. So you have a query ID. Query ID is this one. So if you see in your Dropbox something like this, that's the query. I think you can use Elasticsearch to do those queries, so you don't have to do them manually. You can just do some match or query in Elasticsearch for this text. That's the query ID. So in here, you're going to have to present a text file back to us. That's a query ID, your name. You don't have to put the full name, just your first name or something in the team. The document ID, that's the Elasticsearch document ID, could be the URL or the canonical URL. And the grade is 0, 1, or 2. Okay? So again, while you're not doing this now, you can take a look at this to see how that interface for homework 3 is going to serve this purpose. And if you use one from somewhere else, again, in the past, we asked each team to write one, but since we're so pressed by time now, we're not going to make a big deal out of this. The focus of this homework is understanding the evaluation metrics, not the interface where you click on 0, 1, 2. The very good interfaces, the ones that everybody's using in any sort of, I don't want to say commercial environment, but I want to say where money matters. Like in a hospital, it's not a commercial environment, but you don't want to ask a doctor to read irrelevant things. The recent improvement to all those interfaces has been highlighting, if this is my query, and I'm getting to see some documents related to my query, what everybody wants is the query words to be highlighted in the document I'm reading. Or even a function that puts me directly to the highlight. I mean, Google does that by some extent. See when they pull the snippets are designed in part to say, maybe you can figure out if the information you want is here just by looking at the snippet, right? I mean, you may still want to click that link, but the decision whether to click or not, it's supposed to be in that snippet there, so you can tell, I don't want this link or I want this link. And sometimes you don't even want to click it because the relevant information is in the snippet already, so you're good. So that's the other thing that can be done here. I'm not sure this may be extra credit. So I'm not sure if we require snippets for those documents that you display. If we do, I'm willing to make that extra credit. Again, I don't think you have that much time, but snippets are very useful. Snippets and highlighting is what makes this annotation much faster with text. This is very specific for text. If you are to judge images, if you're familiar with the Crowdflower or Mechanical Turk services where you can just annotate anything you want, images would not require these technologies, highlighting and snippets. You might show the image and ask a question about it. But text, it's a lot faster if you have a pointer to where to look. It could also lead to mistakes. Suppose I see a long document, I have a query, listen pops, I see a document that's long, and I see a highlighting that highlights a paragraph that happens to be not good, not relevant. So I'm reading that paragraph and I'm saying, I don't think it's good. I'm very tempted to say now, okay, 0, right? Document is no good. But the truth is, maybe my highlighting didn't work properly, and I just read a snippet that's not the best snippet or paragraph from that document. So the theory says, if you see a snippet that is good, you definitely can annotate the document to say, okay, that's a good. If you don't see a snippet that's good, you should click on the link, read the document, and grade it accordingly to what you read. But this can be hard. The document, especially the documents are long, this process can take a while. I'm more familiar with annotations in the medical domain, where the difficulty is, so the simplicity is that a lot of the documents are the same and repetitive. If a doctor does a certain procedure, it's very likely to do that procedure in many patients. And the coders, the people who read the notes and decide what codes to submit to insurance companies, because everything billable is a code. Those are very familiar with the doctor procedures, so that's easy. The hard part is that some of the codes are extremely similar to each other. So deciding is it that code or that code sometimes can be a very tricky business. In fact, some of them could maybe, if we are two coders, I may put a code and he might put a different code, but they both reasonably, each one of them could be reasonably used. So those differences are nuances that I think the government had to step in to prevent lawsuits between patients, hospitals, and insurance companies. They say small differences are not, you cannot sue for small differences, because otherwise there'll be a lot of lawsuits about, you submitted this code that has a billing value, but there was a cheaper code that you could have submitted, and then the interests are hospitals want to submit the most expensive codes, right? The insurance companies want to get submitted to the lowest codes. And the patient really doesn't care what code gets submitted as long as, they get, in terms of getting well in the United States, then that depends on billing. So that's another thing that the government stepped in. The procedures doctors do cannot be motivated by the billing systems. You can get a surgery even if you don't have the highest insurance. But the patients care about what they end up paying at the end, because they might have to pay something. And that may depend on whatever code is submitted. So I'm familiar with that process. This is a specialized process, the same thing like law review, where a lawyer is assigned to look through documents for certain things. That's effectively an annotation process. Specialized processes are different than the general process that you're going to do. If this is a general query, and you guys have things like World War II and maritime disasters and things like that, this is something like any person that's educated, been through college, understands what's about and can judge the document. Same thing like an image where I have a tiger and I have to answer a question about what color is that tiger in the picture. Specialized annotations like hospital billing data it's a long training process because general population, people cannot annotate those things. So by the way, this is a much bigger deal now than used to be for commercial companies. So you're Facebook or Google, or not Apple. Apple has different problems. Microsoft, right? You serve a lot of content, even Netflix. Amazon, right? You serve products, but how do you judge the quality of those things? I mean, people do put reviews, right? And there's companies specialized in surveys, right? They often now, I think every interaction you have with a big company, especially customer service, almost automatically you get a survey after that. Tell us how it was, blah, blah, blah. Still, I think there's a lot of money poured into how do we judge customer satisfaction or value of a product or quality of our search if you're Google, how well we do documents. And part of that process is how do we collect all these annotations and what do we do with them? So before we talk about this though, one more thing. This is the last core IR homework. So the homeworks 1 to 5 are core information retrieval. It's what you absolutely must know if you go to a data interview and you are asked about information retrieval. If you say, I don't know what BM25 is, I don't know what an inverted file is, I don't know what average precision is, that's what we're going to study in evaluation. I don't know PageRank or WebGraph, never heard of these things, you're out. Okay? So any such thing means out. Core IR, if you go for any job, interview, internship, even discussion with, and you're supposed to know to have taken an IR class, right? This is the 5 things that you absolutely have to know. Now, after this, presumably we're going to finish this before the term is over, right? We still hope, right? If we do so, we're going to do some things that are kind of my selection of what I think are interesting things. Things like topic modeling or machine learning applied to IR. But we could do instead NLP. We could do so many other things that are like special topics, and you could do those maybe in a different class. In a machine learning, you can have an application to add. But the first 5 things we gotta get through, or else we have a problem. So I'm gonna do evaluation today after the break. Before that, I thought since I'm way more advanced than you guys with the lectures in front of the assignments, I thought of showing you another paper and talk a little bit about something that goes more into the research side of things. Last time, we didn't discuss full details of that paper, but we get a little bit into how to make this comparison, why things matter. So these people here, there's a famous phrase by now called 6 degrees of separation. You guys know that one?
Yeah.
Right? Many people studied the problem of social network before social networks came along, right? So there were these philosophers, intellectual linguists that talk about that. Now this is I wouldn't say very recent, but reasonably recent paper from 2012, 6 years ago, that I picked not because it's famous, but because it studied the Facebook graph. Just when Facebook massively changed. Facebook, like a lot of those very successful companies, had a relatively, startup associated with a university, I think it was Harvard University, and they deal stuff with pictures, and they were very concerned about college students, and out of the sudden, I think in 2007 or 2008, boom, it expanded to non-college students. I think it was 2008, maybe, and it happened. The reason some companies are extremely successful, like Google, Amazon, Facebook, is that at some point they provide to the society something that it's missing and needed, And most of them don't realize right away that they are providing that service. That's what happened with Facebook. When Facebook opened up, the creators of Facebook thought about it like in the college sense. That's how they created it. So you can see the next door girl's pictures, right? Who's next door next to me? That was they don't say that, but that's how it was created, because people who go to college, young people, they single and all of that, right? That's how they thought. How about we open to more people around the campus, so people that come to campus may not just who's my next door, but who's around Boston, right? They didn't realize that actual society needs a social way to make connections, even with family, like well-established people in your life. We're not talking about new friends around the block, because they go away, you can maintain this connection, and Facebook at that point had a very easy way to update, see my nephew's pictures or something that was missing. Later on, they realized this thing. So that's what Facebook makes. So there's a different graph. The first observation we need to make, the Facebook graph, you don't have to take notes. It's not the same as the web graph. So few obvious differences are, let's take some cracks at it. Why are they not the same?
There's no such thing as outtakes and
There actually are, I think. I think you can be my friend without me being your friend. Is that possible? Yes, but that almost never happens.
Not in it, people
But you can follow.
Right. I think you can have a directed link, but in practice, 99% of the links on Facebook are reciprocal, right? So that's one thing. It's directional. What else? I'm gonna add one. It's much more personal. Whatever page you have, like your blog or my website, right? I edit that page, or I don't know, my corporate website. It's never as personal as a page about me, Facebook, right? Like where I am, where people see what I've done today, where I post notes about what kind of crazy stuff I've seen. But that's way personal. It's about the individual, not about some particular topic. Like this website is about the course, right? It's written by me, but it's about the course. What else?
Is it very connected? Does it connect everything?
So that's what this paper is trying to do, connectivity, how to measure connectivity in a Facebook graph. But how is different the web graph than the Facebook graph? So how do we think those graph looks like? What's a typical connectivity for a Facebook node? So this is a node in Facebook. And this is a node in the web graph. What's up with the number of links in here? Do you guys know how many friends one can have on Facebook max? Is there a limit? It is.
There is.
Nobody knows it? 5,000, right? So these are, how many degree. And these are two kinds. Let's say these are, this is, let's say, degree in degree, out degree. How is the degree on Facebook usually looking like? Pick a random person on Facebook. How many connections that person can have? Of course, it's a variation, right? Some people, very few people have very few friends. I think it's rare to see a person that only has 2 Facebook friends, right? Most people have friends from whatever, their neighborhoods, their work, their actual friends, their family. Very rarely see somebody with very few friends, right? And there are some who have a few thousands of friends, which of course, most likely you don't even remember who those people are, right? My wife, I think, I don't have a Facebook account, by the way, never had. I never needed one, but my wife does, and she has like 3,000 friends. And sometimes I ask, do you know who those people are? If I put one of them at random, do you know who this person is? Probably not, right? But anyway, they say friends. So the degree, what's the average or median degree on Facebook? Take a guess.
hundreds,
Yeah, but how many?
300 to 500.
That's what I would guess. I guess there are some exact numbers. This paper is not recent, it's 6 years ago, so we can't go by this paper. But I'm guessing this might be around 250 or 300, an average number of friends. How about here, if I take out a website, how many pages do I have in links and out links to average?
50 to 100.
Huh?
50 to 100.
I don't think there's 50. If I'm to guess, we can check that. If I think it's about 20, maybe. Of course, there's variation. Which one offers more variation? Variation, I'm going to change soon for variance. We know variance. So variance is what? Measures the, right, it's the square root of standard deviation, but what does it measure? When a distribution of values, like degrees, have high variance versus low variance.
When the variance is like, if the distribution is closer to the mean, then it.
What do you mean? The distribution is a bunch of values.
Yes.
What do you mean closer to the mean?
I mean, it just says the distributed the data points.
Most values are close to the mean.
Yeah.
That's what kind of variance? Low. And if there is a lot of values far away from the mean, so the mean might be something, but a lot of values are way low and a lot of values are way high, that's a high variance distribution, right? So if I look at all the degrees, that's a distribution of degrees, right? Or a histogram, because I can count how many degrees I have. And if I look at all degrees here, which one will have more variance? Facebook has more variance or the web graph?
Web graphs.
Maybe you guys can study this problem. I think it's the web graph. But, I think there's a lot of people here that are, I'm guessing right now, but I'm guessing I have educated guesses because of my, research that I'm doing, but I'm guessing that most people are around 200, 250, 300, and that creates a rather lower variance. While websites, there's significant number of websites with very few links and significant number of websites with a huge number of links. So what do we care? In the web graph, we say we have what? We have PageRank, maybe, and let's call that PR of a page. And in here we have hits of that page, hub value or authority value. And we can, there's algorithms like we've seen last time to compute those. How about here? Can we take those notions? And is there a PageRank notion on the Facebook graph? Or a hit notion or authority notion? I mean, would that be something to care about?
Maybe you search for something then.
Do you mean by hub and authority links, kind of?
I'm talking technically, but also pragmatically. Like there's the mathematics of how do you take PageRank and make something out of it on that graph. But then there is the purpose of it. If I have a PageRank value, would it be useful for Facebook users? The PageRank value in the web serves as the importance of a page, right? Why would we need an importance of a page for the Facebook graph?
Because it might be useful in case you want to advertise something. Person who has
Suggest
large
to
number of
users like which businesses are around, like which businesses they would like to see.
target.
Yeah, so first of all, you have to realize how people use, the individual users use those graphs very, very differently, right? In here, we almost never go to a page. We almost always search, and then in search, PageRank presumably plays a role, right? Because it tells me what things I look for. In Facebook, do you guys search? I mean, are you guys active Facebook users? You check Facebook once a day, say, or once a week at least? No? No. Yes? When you do search, when you search, you actually know where you want to go. You type somebody's name in the search box because it's easier to go that way. But it's not really a search. You know exactly where you want to go, right? So Facebook that has very little search value in it because for regular users, you don't actually search for results. The web graph has a huge search value because you often don't know where to go. Right? So I think these measurements are not the actual importance values, if you like, although I think they do measure things like followers, right? In Facebook we have followers. That comes from Twitter, actually. They're the one who started the thing with the followers. Is followers an approximation of page rank? I say, how many people follow my page? Is that an importance? Can I say that's an importance
You
value?
call it as a hub then. Person who has many followers.
As a hub, I think that's an authority maybe. Because if I have a lot of followers, what does that mean? It means people trust or like what I say, right? So who has a lot of followers? Maybe LeBron James, right? As a hub, I think people use their own page as a hub most of the time. I don't think most people use other Facebook pages as a hub. And if I'm to have a hub of, say, all the construction companies that I can use, typically those are not on Facebook. There's other hubs that have links to Facebook pages. So the number of followers and the authority score, so authority score might be some importance of how a particular page it's important to other people. Everybody has their own page important to themselves, but the question is for others, how important is my page? So what do people study on these graphs? If you are now not a user, you want to do a social media study, you are either a company, or you are a community of people, or you are a data researcher, or you are somebody working for Facebook. What would be interesting there? So let's look at the title, 4 degrees of separations. What do you think that means?
That how many person you know to know somebody.
How many hoops do you
Yeah.
through friendships you have to jump through to get from a random X to a random Y? So people have studied these things in other contexts, and they found out that there was 6 before social networks, and after social networks took over Facebook. Let's say it's about 10 years old, because it really started to be available for everybody in 2008. 10 years, it's only 4. What does that mean? Why was 6 before and now it's 4?
More connected.
More connected, right? So I think it has to do with the fact they actually run experiments before Facebook. The initial experiments of this kind have to do if you have to send letter to your friends or family, and you have to reroute them through the nearest family member, so to speak. So if I want to send a letter to my mother in Romania, I don't just put it to the mail. I look for a jumping connection. I send it to somebody which I know in New York. That person travels to Romania, gives it to somebody in Romania who they know, who happen to know my brother, who give it to my mom, sort of thing. So they actually run this experiment and establish the 6 degrees of jumping around. With social media, it's only 4 because we have a lot of friends, much more than our actual friends and family. And like I said, people have 2,000 to 3,000 friends, they don't even know who they are. And those establish a lot of connections that you are not aware about. In fact, did you ever notice how Facebook sometimes pulls, when you look at the Facebook page, pulls a, you might know this person, and you happen to know that person? How do they know that?
Common connections.
Okay.
Because they look at a graph and say, there's so much connectivity between you and this person. You might know it, and you do know it, but sometimes the connectivity that they use to make this connection, it's actually hidden to you. You didn't know that my friend knew a friend who knew this person. We didn't know that, but somehow this hidden connection pull up that thing. So what can we look at, these 4 degrees of separation? There's all kinds of notions here, like diameter of the network and connectivity and degrees. So what do people do? This is in 2000, the data comes from, so this is 2012, the data is from 2008. Let's see quickly. data. And look at the plot. Yeah, maybe it's 2008, I think. So that's what Facebook really started taking off. So what they did. Let's look at 720 million users and 69 billion friendship links. I think Facebook is about double that today. Is it bigger than that? Bigger?
In terms of users, yes.
How big is it?
More than a million.
Yeah, I'm saying double that.
Okay.
Is more than 1.5 billion today? I don't know. I think it's double, roughly double. And a lot more friendships. Okay, some related work here. So they, I think by time, they discovered that if you go back in time and you look at, I think those are ages, the friendships, and these are the users. They say the relationship between this as time evolves, the more users I have, the more friendships I'll have, right? It's like a power law. Remember those Higgs laws that we talk about with certain coefficients? So it seems to go that way. And so suppose I want to analyze the Facebook graph or some chunk of it. There's several difficulties. One is, so there's the concepts of neighborhood. This is essential for any social graph, the concept of neighborhood. Many data mining, in a data mining course, as soon as you talk about KNN algorithms, you have a neighborhood graph, right? So I think the way it's defining here, this is NG. I'll skip G. G is the graph. So T, I think, is the pairs X, Y such that X or Y reachable from X in T steps or edges. And I can have NT, well, let's put a T down. NT of X could be the same. What I can reach from X in T steps. So T, I mean by steps, jumping over a friendship. So I'm friends with him, and it's like in BFS. If some Y's can be reached in one step, they count as wave one. Everybody's reachable in one step, it's wave one. So to say a particular node or user is wave 2 node, it means it's not reachable in wave 1, but is reachable in wave 2. So these measurements show that the Facebook graph is roughly a 4 connection graph. Most of the pairs are reachable in within four jumps. While that seems very small, 4, right? It's not that big. Remember this, most of the connections people are unaware of. I need a lawyer today, and that lawyer is, according to Facebook, 4 jumps away, right? So I know somebody, which is my friend, who knows somebody, who knows somebody, who knows the right lawyer. But I don't know how to get there, right? I don't know who to ask to get that. You know, I'm not aware of that connection. So what's the difficulty here? There's 2 difficulties presented in this paper. So a technical. Graph compression. Representation. And approximations of neighborhoods. Now, this is something that we did very little, so it's something that we're probably gonna skip, just give you an idea about. But this, if you take an algorithms course, is the same problem as identifying all sequences with the particular problem. So typically, when people give examples of NP-hard problems, iterating all sequences or all subsets that say sum to a value. Find me all the subsets, I have a set of numbers, find me all the subsets that sum to 100. These kind of problems are NP-hard, but they can be approximated with algorithms that cache. If you took my algorithms course, we mentioned one of these problems towards the end of the course, where there's a bunch of lists and we truncate them. This is the problem here. So in terms of approximation of neighborhoods, here's what happens. If I want to go from B to a radius, I guess this is the B of xt. It's the same notion here. So if I want to go from X, jump R steps, how do I get there? Who's in that neighborhood? Well, it's everybody who I can jump to, and from that point Y, jump R minus 1 steps, right? So if I want to say, where can I go from X in 5 steps? I say, go everywhere you want from X, everywhere you can, and from there, go 4 steps. This creates a dynamic programming type of methodology, right? If I could somehow represent and list down those balls or neighborhoods for radius n minus 1, I could quite easily iterate through them and compute the neighborhoods of size r. Again, if you remember the shortest paths problems or this kind of problems, the way they solve the paths within edges of 2, and then having all those paths, I deal with paths that have edges of 3, and then paths that have edges of 4, and so on and so forth. So that's the same kind of idea, except the balls get very many and very big. So balls in here, ball stands for a subset. It's not a geometrical ball. It's a set of reachable nodes within so many steps of the center. Those sets serve as subsets, right? These subsets of users with a lot of overlap. And it's hard to represent. There are many, many of them. So it's the same problem like in here. If I want to know, not in here, if I want to know, I have a set of numbers. How many subsets sum to 100 or at least 100? I could think about it this way, how many things sum to 2 or 3, and once they sum to that, by adding a value, now all of them sum to 3 plus that value, and keep building that, the algorithm being very easy. But the number of sets or subsets I have to keep track on becomes very large. In some sense, the classical 3-SAT problem, satisfiability, no? So that's one of the things that if you ask an interview, what's 3-SAT, and you say, I don't know, you're out. I don't want to be that bold, but it's a classic thing. Satisfiability, 3 CNF conjunction form. I mean, you don't have to know the theory, but it's a kind of one problem that 2-SAT, it's very easy to solve, and 3-SAT is impossible. So things like, just a quick parenthesis for whoever has seen this. The question of 3-SAT, I have a bunch of literals, A or B or not C, and, this is an and, D or not A, not B, and A or not B or not E, and. So, or means you have to, one of them has to be true, and means one of them has to be true in every single clause. Can you find an assignment of all these Boolean variables A, B, C, D, E to satisfy all the clauses? That's 3-SAT problem. Something that people who study logic early on in their education, like in Asia, they do problems like that even in the secondary school without calling them complexity problems. What you have to know is that if you have this is 3 CNF because every conjunction has 3 literals. If you only have 2, it's easy to find a linear time algorithm who can make the assignment. But if you have 3, it becomes impossible. The reason is you have to keep track of too many subsets, right? Suppose I find an assignment that satisfies these 3 clauses, right? then many possible assignments who satisfy those. If somebody add the clause to it, say something with X or not A or not, I don't know, D, I could say which ones of my assignments so far that satisfy those clauses happen to satisfy this one too, and I'm done. The problem is the number of possibilities to satisfy those clauses might be gigantic. So it's the same kind of an easy algorithm, but the number of subsets that I have to keep track on becomes intractable because it's exponential. Same thing happens here. This is a simple dynamic programming algorithm if I can keep track of all these R-1 balls. So there's two things that are happening in this paper. One is, how do we keep track of this? This is an algorithm they call hyper-NAF that estimates the size of the neighborhoods. It's not exact, but it's an estimation. And they prove that while the estimation is inexact, it has good statistical properties. If you look at this equation, this is one, this is what we want, right? We want the expected value to be close to the true value, right? And then this is something that goes to 0 perhaps, so it's very small. So there's a statistical bounds that say my estimation is not very far away from the truth, at least on average, right? So there is this, and the other part that is necessary, the problem with these graphs uncompressed is that they're huge. Even if I have an algorithm or an approximation like A and F, this algorithm, how do I even load this graph into memory? So these are the two big problems. This here is this A and F algorithm, but what about this? So in here, we didn't talk about compression schemas for graphs, but there's some things that I think you can relate here. You can relate to something we talked about at Lempel-Ziv and at Hofmann codes. Right? So here are three ideas for how you can compress sequences of neighborhoods. And we're not going to really understand the details, but maybe they sound close to Lempel-Ziv. So they say one idea is, if I already listed a similar list of neighbors or users, which happens a lot, by the way, in IR, if I pick a particular, in Facebook, if I pick a particular community, Northeastern University students that are in computer science, a lot of you guys gonna have a lot of friends in common. So remember what Lempel-Ziv did? It says, if I see a sequence that I've seen before, instead of rewriting down that sequence, I'm going to point out to say, you've seen this sequence 17 steps before. That's what this step is here, is in effect. It says, if you've seen that list of users or neighbors, instead of rewriting it down, copy a link to it, and then make some changes. And I think that works well for Facebook because you can say a lot of these people here have common friends. So instead of rewriting those friends as a adjacent list for every single user, you can say this is a community and everybody's friends with everybody. Because that's not really true, so you have to make some adjustments. Then this is an idea of seen in indexing. Instead of recopying a list of things, we can say there's an offset and a length that says copy from that offset that many bytes. Of course, this is not an offset in bytes, but that's what it is as a representation. It says it's the same idea that you use in homework 2, where you have to keep track of where something starts and how long it goes. Right? And lastly, here something we talked about at indexing that says when you have to write down a lot of things, it says you have to keep track of the deltas between them rather than the numbers themselves. So I know this is not really working for the Facebook graph, but those are the three ideas that I use for compression. They have an entire paper on a compression schema for social network graphs. And not just them, many people try to do that. So I think some of these references will contain a schema that says, how do I compress or re-represent, encode a graph in a way that when I use an algorithm on it, just like with inverted index, I don't have to decompress it. So the issue here is not so much the losing, the JPEG compression, losing information. The issue here is more like the inverted file list, where I want to represent it in a way so my algorithm can use it without loading, expand the whole thing in memory. Those are technical difficulties. Once I do this, another step that they do that I'll be honest with you is not very clear to me exactly what they mean, is rearrangement of the graph in a hierarchy that makes compression easier. So this LLP stands for a rearrangement of the graph. If you look at the graph, a graph can be arranged in a hierarchy in many ways, right? Every node I pick as a root, I start from there and I arrange in a hierarchy if I want to, right? So I can pick any node and arrange it as a root, or even sometimes multiple nodes. How should I arrange it so that compression is easier? Compression by my compression schema or representation. I'm not sure how this algorithm works, but I can see why a certain arrangement allows for a better representation. But it's not clear to me how to do this LLP step here. Okay. So once we have all that, they also mention how much of a machine they have. Are there? I think something like 100 GB of RAM machine. This is a encoding rate. So Facebook is the original graph. The two numbers is, if I take without this LLP step, without rearranging the labels in a hierarchy, and I do my encoding schema, I compress it, are those numbers in gigabytes? No, bits per link. So I guess this is how many bits I end up times 69, what did you say? 69 billion links, I think. So if I multiply this, I get the size of the graph. And that's an 86% of the original. And once I rearrange the graph, I can get a better compression. But let's look now at the main results. So what is this? It's number of pairs, X and Y, right? How it's reachable. And this is the number of links that you need to get from X to Y. So this is a histogram, right? What do we see? For most pairs, you need 4, right? You need to jump to 4 hoops. For some, you need 5. For some, you need 3. But everything else, other than 3, 4, and 5, how many pairs have a connectivity of 0, 1, 2, skip this range, 6, 7, 8, 9, 10? Almost 0. So this is a very sharp at 4, 3, and 5 around there. Right? You can see everything else is flat compared to the full size. So if you just say, how many people are my direct friends, they'd be like 100 or 200, and everybody has 200 friends, but that's not that many links compared to the links you can jump through 3 or 4 things. But once you get to 4, everybody who's here at 8, remember, it's at 8 because it was not earlier. So this is like BFS. If a link, if a pair XY is listed at 8, is because this is not reachable from X to Y with fewer than 8 steps. If it's reachable in 6 steps, it will be at 6. And by the way, what are those IT, SE, and so on and so forth? These are subgraphs of Facebook. Facebook is the whole thing. I think US, it's the United States Facebook. IT is the Italian Facebook. Switzerland Facebook. And IT and SE is the Italy and Switzerland together. So those people are from Europe, and I think one author was from Italy, the other one from Switzerland, and they chunked the Facebook. I think the FB stands for the whole graph, and then the other ones for subgraphs. So here's the degrees of the data sets. Degree means what? Roughly number of friends, I guess, right? Of a node. Average, sometimes you have to know the difference between average and median. In many cases, maybe those are the same, but sometimes they're not. I don't know if they really mean average or median. Let's say they really mean average, that is average. So what do we see when Facebook, what happened in 2008? Facebook became a social network, not just a college network, right? So what happens to this average degree? Why is it that in 2008 people had 6 friends? Oh, let's take the actual Facebook. So what happened here is really here, the problem is, so Facebook in 2008 or so was already a social network in US, but not in Italy. It first became in the US a phenomena, and then it took, I don't know, 1 year or so to move to the rest of the world. I think that's what happened. So my point is that before taking off, it was a very small network per user, and out of a sudden it became everybody you know was on Facebook. Even, like I said, some people you don't actually know, you're friends with them now. The current stands for 2012 or so. So I guess the average number of friends is 200. Was 200, maybe now it's a little more. After 2013 or so, I don't know when the IPO of Facebook was, maybe 2014 or 15. Facebook became much more an ad-based company. So a lot of the pages and a lot of the linkages in Facebook are now commercially motivated as opposed to friendship and family motivated.
Why is there a decrease?
From here to here? Either there was some sort of problem, like recently there was a problem with Facebook. I don't know. I think there was some lawsuit initially. In a movie, I haven't seen the whole movie. There was a movie a few years ago. Isn't there a lawsuit about Facebook when it was not clear what's going to happen with it and they had to get a settlement? That may be one reason. I'm not sure. Another one may be, I'm not sure how the crisis in the United States affected people. That's about the year 2008 when the financial crisis hit the US economy. So I'm not sure how that played out with Facebook. We can try to look at that.
Or is it that there were too many people, so but the decrease of had a large variance, that's why
Maybe-
the average
maybe-
might,
Right, when they expanded. So what happens, this was mostly a college network.
yeah.
And when they expanded to everybody initially per user, there were not that many friendships. That's what you mean, right?
Yeah.
Maybe that's the explanation. That initially when people get to Facebook, a lot of people got to Facebook in 2008, 2009, but they didn't have all the friends at once. They started with a few friends. So it took a while to build up the network. So then what else do we have here? These are the number of users. So this last one is how many users are on Facebook and how many links are there, friendships. So how is that different from 2008? In 2008, the Facebook network, we could have run graph algorithms on our laptops on it, right? I mean, our current laptops, not the ones from 2008. If I give you 50 million links, maybe you need more than a laptop, but still would be doable. 50 million users. I think the only thing that you have to know in here to read this paper is is a measure here. I think it's called the speed or something like that. Different fields call this differently. Is the ratio of variance divided by the mean. So you have to be statistically aware. I think you guys are of mean and variance already, but what's up with this speed thing? Why is this a thing? Can we, so think about the distribution, any distribution. What happens if I multiply it by 2? Every value in the distribution I multiply by 2. What happens to the mean?
Remains the same. Increase by 2.
So I take everyone's age in this room
Increase by 2.
and I multiply by 2. The mean multiplies by 2. What happens to the variance?
Remains the same.
Okay, you guys need to go back to the statistics. I'm not gonna ask the question then, so you guys have something to think about. If I take a distribution and I play with it, what happens when I add a value? I add 25. What happens to the mean? I add 25. What happens to the variance when I add 25 to everybody?
Does not change.
It does not change. But what happens when I multiply by 2? With the variance. I think so. So this is an important metric because when things get bigger, the variance is expected to increase too, but not linearly. So if this speed value, it's characterized as differently distributions of big values, say like salaries. Salaries are in hundreds of thousands of dollars or so, right? Versus ages, which are years. So they have some metrics corresponding to the speed in here. So you have to know at least what that is when, let's see, it's a table or something like that. Is it here, I think? Well, the average distance is this one. That's the actual how many loops you have to go through to reach. You can say it's pretty flat, except for this value here. In Italy, there was not really a Facebook in 2007. Everything else seems extremely flat, around 4 point something. I think that justifies the results. There are really 4 loops to jump through. So apparently, their point is the world is, even though the number of population in the world is massive now, it's actually much more connected than it used to be before the social networks. Right, so here's here, index of dispersions. There's many names for this metric. Variance divided by the mean. Okay, let's take a break now because I'm done with this, and then I'll start talking about evaluation assessments. What's gonna need to happen for Homework 5.
Share the public key with you.
Okay.
Maybe we can access SSS.
SSS.
And you can set it up yourself. use the Google platform.
Even I already used Amazon.
Yeah, but it has money. And it's free.
Okay.
If you set it as a try to do it off the class. We'll try to set it up off the
Yes,
class.
I mean even AWS, I guess I still have money. Free one.
But you can just create new accounts and use three.
But then you get what the basic account.
Yeah, basically.
And then if you apply now, it will take days until they approve for you to get your good account.
Not sure, but any normal account has.
Oh, yeah, I mean, yeah, if you want.
Ask what you wanted.
Yeah, we did it on my dishwasher.
Dishwasher, sorry?
It's a specific service, like, if you do AWS,
Okay.
they publish their IP address range, and so if you're crawling on AWS, some of the websites will just block
Okay.
that range.
Okay, that's fine. I mean, otherwise,
And then so, yeah, then you have a server out on DigitalOcean, and just,
so this is easy to install.
DigitalOcean, that's not easy to, it's just like a big server.
Can you show me?
Yeah,
There are few years
yeah, so the very religious sites, there's no
Okay. Is it the basic machine or anything else? Sorry?
8 gigs in memory.
8 MB. Okay.
They have some free stuff going on.
I think we can do up to 100 feet.
Okay.
Yes.
Thanks.
You can get the pay. I think AWS is fine.
And anyone can do the first step. You set up today. We'll see. Let's see if we have any.
Professor, for the homework 3, is there a way to decide that your crawler has done a good job?
You have to pick at those documents. That's the point of putting a query and see with the interface on top of Elasticsearch what you get. You should be very happy with the top results of these queries. If you got what's your topic?
Nuclear catastrophes.
All right, so you type in there something like Chernobyl. That's one of the subtopics, right? If you see top 20 results about Chernobyl,
Okay.
It means, at least from a focus top crawl perspective, you got some good documents.
Okay.
If you see you type something Chernobyl and nothing comes up about Chernobyl, then you know for sure it's wrong. What you can do is a test that I think makes more sense. Here's how we do it. The URL seeds are generated with these subtopics or queries in mind, like Chernobyl. But there are some nuclear accidents that are not the obvious one listed in your team, either you or your teammates, right? So there were about 7 or 8.
Pick some few extra links.
Pick some other one that's not obviously in the
Yeah.
top URLs, and you should have gotten through the crawler. You should have got to all major nuclear accidents, right? That's the point of a crawler. And if you pick some other accident that's not listed in the original URLs, then means it kind of worked. Same thing with you got shipwrecks.
Yes.
So there's 2 or 3 shipwrecks that are listed in the top URLs, but there are many others that are not.
Yeah.
So if you type there Titanic, I don't know, and you don't see anything about Titanic, there's probably a problem with your crawler. He's got the Italian ship that crashed in Italy a few years ago and something in Korea.
MVC. Yeah.
Right. So this is the recent one, but there are many ships that crashed. So I think the easiest way to check is to put related queries, but not that you know you should get relevant results, but not the ones that you started with, because those are there. It's by trial and error. There's no way to do this, I don't think. Like, what does it mean good? You crawling as a team, what, 60, 70,000 documents?
I mean, after merging, it will come down to like 40 to 50,000.
Still, you should have, for a query that's related to your nuclear accidents, at least 1,000 good results, right? If I type something like atomic bomb or Hiroshima or I don't know, nuclear fusion or something like that, and you have nothing, how is that possible out of 50,000 results to get nothing for a related topic? Right? But if you get the top results good, at least you know.
Yeah, that's what I want to know, like what percentage of the crawl documents should
It's
be
hard to
related
evaluate, but in Elasticsearch you can type some queries. For you it's easy because nuclear is a very specific word. For him, I guess it would be something like shipwreck. You type shipwreck or something like that. How many of your documents contain the word shipwreck in them? That's a good gross approximation. If I have 60,000 documents, 20,000 are about shipwrecks. That's good, right? You can type something else like, I don't know, treasure finding, disaster like hurricane disasters, who knows. In your case will be some other things like atomic developments. There's this commission that checks nuclear weapons everywhere. This is a United Nations committee, IEA.
I guess so, but it's all secret in the name.
No, I mean, there's some things related to nuclear that if you type them in, you should get a nice like chunk of documents related to those terms. I think
because
that's
my last few thousands, very few were nuclear related.
all of you would have about half, unless you do a very aggressive frontier management. About half of your documents are probably junk, as far as the topic is concerned. But that's okay. We don't expect to have even more than 15% on topics. So if out of 60,000 you got 10,000 about nuclear things, they easy to search, you know. What did you get?
World War II.
Okay, same. There's so many subtopics and queries you can put about World War II that are disjoint from the original URLs. So you got there some big battles or something like that, but there's so many events related that you should got something in the index related to those events, right? Even though you didn't start from this event.
Yeah, I was getting some World Cup stuff for a little bit.
Yeah. So if you get out of 60,000, 70,000, 10,000 documents about World War II, that's good. All right. So evaluation. I want to show you a few plots first. What we want is something like this. Now this is me writing on top of a picture here, but the effect of annotations and judging is you get a list of results, right? And we want to mark them. In your homework is 0, 1, 2. In this one is binary. R stands for yes or relevant. Yes or 1 or true, right? All those things are equivalent in binary world. Yours is not binary. the one that you have to do is not yes or no, like here. It's 0, 1, 2. 0 should mean clearly not relevant. 2 should mean clearly relevant. 1 should be related but not relevant. Now 1 is a foggy notion, and it's even worse in reality because it's 0 to 4 or 1 to 5. So a typical question that you can get at the interview these days is what's the difference between Netflix recommendations, say, or products between a 2 and a 3? How would you define a 2? How would you define a 3? Like with 5, when you put a rating, why you put a 3 instead of a 2? How do you think of that, of those ratings? And I think I mentioned last time, most people, by trial and error user studies, find out that it's actually doubling or exponential in any case. Like something you rate as a 3 is twice as useful as something you rate as a 2. Maybe not twice, but there is an exponential scale. Maybe it's 1.8. Anyway, in here, simpler version is binary, so we don't have to worry about how the scale works. It's either white or black. And since I have the projector on, I'm going to show you another picture with some interfaces that students in our labs and others use for evaluation. This is for mechanical Turks, but you would create one starting with a visualizer. You would so in here, where is it? So civil war battles in South Carolina. You would see a document. The document is not present here. You see the document, and this page is asking you to point to one of those things. This is a scale of how many things? 0, 1, 2, 3. So instead of 0, 1, 2, it's 0, 1, 2, 3 here. It tries to define for you the scale. So I said it's typically exponential, like double the previous one. In here, it actually defines the scale. So you could, in a certain context, do this. So non-relevant means totally junk. Relevant means that page has to do with the topic. Highly relevant, it says here substantial information. The problem with words like substantial information, it's still down to the reader to judge what's substantial, right? I mean, this is presumably non-substantial, and this is substantial, right? So what's the difference? I'm going back to my question. What's the difference between 1 and 2 here? It's still down to whoever reads to decide what means substantial. This definition, I think it's not that good because it doesn't actually force the user to make a decision, a consistent decision. It led it to the user to decide what's substantial. So what you may think is substantial, he thinks is not substantial, and now we have inconsistency. Typically, this is a very hard thing to do. For a query that is not quantitative, you know, if I ask what's the range of salary, blah, 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 from 0 to 100, low, from 100 to 200, medium, from 200 to 300, high. That's a well-defined scale, nothing to interpret. But in here, things like substantial, minimal, authoritative, it's still down to the whoever reads it to figure out what that is, right? What's authoritative? Okay? Here's another one that a student graduated now created. This one is a different purpose, but still an annotation tool. What this one here does, it shows you two documents. And it says, which one is better? Instead of evaluating things on a scale 0, 1, 2, 4, recently people have moved for evaluating a preference because they find out through user studies that preferences among people are far more consistent than scale. If I say 0 to 4, let's rate movies, you're going to rate more low, more high. We would have not consistent scales. But if I ask, let's rate orderly the movies, like let's put them in the order of preferences without assigning a scale. You just say which one you prefer to which one. Turns out humans are way more consistent in terms of preferences. Maybe you give a movie a 5 and I give it a 3. So we're not the same, but when we talk about is this movie better than that movie, people agree a lot more. So a lot of these evaluations have moved into, forget about the scale 0, 1, 2, 3, 4, 5 and stars and all that. Just give me 2 or even 3 things and tell me which one do you prefer between those 3 things. So what are the options here? Equally good, you like this one, you like this one, or equally bad. Equally bad means they both irrelevant. I can't really compare them because they don't talk about the topic. This is a funny example. This is one of the most impossible things to evaluate, right? So I don't know, there was a conference, there's a conference that have every year tasks like this. It's organized by the people who wrote Trek Eval, the Trek conference. It's organized by the US government, Department of Commerce, for the purpose of measuring stuff. In this case, measuring retrieval performance. So one of the queries invented at some point in the past that became famous by now is creativity. And the question was, find ways to measure creativity, blah, blah, blah. It became famous because everybody thought that's absolutely impossible to evaluate, no matter what schema is, no matter what the grades are, no matter what the order are. This is too philosophical in nature to put your hands on a metric for creativity. But the idea is very good. Comparing 2 documents or 2 images or 2 songs or 2 pictures or 2 books and ask which one is better or which one do you like or which one is more useful for your exam or things like that. You get a much more consistent result than asking 0, 1, 2, 3, 4. Okay. So this is kind of the, something like this you have to have for the what did I show you first? So back to this schema. I'm gonna have to turn that off. The annotation is one part, right? So I'm gonna just say I have some documents like these, doc, da da da, and I have here relevant, which means yes, which means true, which means 1, or non-relevant, which means false, which means 0. In a binary, QREL, that's how those files are called, which are set of judgments. Or you can call assessments. Or annotations. Or labels. One of those things means the same. That's what I have. So let's take this list. R. Okay. So let's say R, 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 N, N, R, N, R, N, N. I've got this list. What I also have is ranks. So this is rank 1, rank 2, rank 3, 4, 5, 6, 7, 8, 9, 10. That's what, you will still have ranks in your homework 5, but you're not going to have 2 values. You're going to have 0, 1, 2, 3 values. Right? 1 is not the middle between 0 and 2. So it's certainly between 0 and 2, but you can't say 1 means half relevant. Now that's what I have. And now I'm going to make a small parenthesis to talk about have people measure retrieval performance. Before ranking. So when IR came along, information retrieval, not the subject, the actual Google and search engines, everything became ranked. Every single result from the very, very beginning, Google came, even before Google, Alta Vista. When you put a query, you get the rank list of things. But retrieval, the process, happened before that, before companies like Google and Alta Vista. There was the whole lawyery thingy, which was, I have a case, find me the relevant, you know how lawyer goes, they find the pre-cases that are relevant to see what decisions, how juries acted, how the decisions were made, da da da. So that's things. Medical domain, the same thing. Find me the relevant information for this. Any sort of library research is essentially a retrieval problem, right? Before Google and Alta Vista, there was no ranking. So how do people talk about, they still have what's good and what's bad, right? So I'm producing a set of books or songs or images, but not ranked, it's a set. So before ranking, that is a set without order. So how people thought about this problem before Google came along in 1997 was, okay, here is the set of truly good things. So these are the true, correct Y. And here's the set of the retrieved things. Retrieved. So this is the relevant. True Y. True yeses. This is the low cases I actually need to put my hands on, or books. And this is retrieved, which is the estimated yeses, or predicted yeses. So people came up with names for all this stuff. The stuff that is retrieved, and it's correct, it should be retrieved, it's in the middle here, right? We call that true positives, because they are positives and I'm estimating as positives. The stuff that it's retrieved, so like an image or a song or a book or a locase or something, but it's not really a correct item. This is a false what? Positives. Because I think they're positives, but they're not really positives because they're not truly correct. The stuff that's in here that it's correct, it's good, should be retrieved, but it's not. My algorithm or my schema missed this document or missed this locase. This is a
True negative.
false negative. Because I think it's negative. I'm not retrieving it. I believe it's negative. But it's not negative. It's actually positive. Right? True yes means true positive. So do I need to write down what FPTP, FN stands for? I think you guys are gonna get the letters right. If you see FN, you're gonna know that stands for false negative. What people have a confusion on is which one is FN. Okay, so it's not the letters that FN means false negative that confuses anybody. It's, is it this one or that one? So false negatives, again, are the ones that I estimate. Let's write that down. False negative. Estimated negative, but truly positive. So I think it's not supposed to be retrieved, but it's a mistake. And what are the true negatives? The ones that are negatives and I'm not retrieving. The outside of the group. So here are true negatives, true negatives, true negatives. Those are all the documents that I'm not returning or producing or estimated, and they're not supposed to be produced. Okay? Very important that this is a set notion. In here we have no ranking. All these items here, whether they're books or movies or songs or web pages, they're not organized in a ranking. It's a set. maybe I should turn this on, turn this off. We don't need it today. All right? So what should I measure? What is good? When do I have high performance? I'm still in the set world. I'm yet to move on the ranking world. But in the set world, when do I say my algorithm is very good? It does a good job. Or my apprentice, like I have a lawyer, junior, say, buddy, go find me all the cases that are relevant to this case. The guy goes to the library for 3 days and brings back a ton of records. When are those records good?
If you get true positives.
If I get the true positives, which means this, well, so how should I say my guy did a good job, mathematically?
The relevant and retrieved also.
So, okay, I want to say the set of relevant set, it's exactly the retrieve set. That's perfect. But this is kind of a conceptual perfect. In fact, there are two qualities here. There's two ways to minimize my mistakes. There are two kinds of mistakes. This is retrieving documents that are not that good. And this is missing stuff. So this is extra. And this is missing. So the two types of mistakes. If I want to minimize the extra stuff, the documents or songs or images that are not good, what should I do with my retrieve set? Okay. The guy, my friend Joe, went to the library, brought back 3 cases of documents, right? And I'm like saying, I think that's too much. You have a lot of extras here. What can I do to minimize the extras? Just get 1 box instead of 3. So if I shrink the retrieve set, I'm gonna kick away some of the false positives too. But my missing stuff will increase. The ones that I throw away will actually be some good ones in there. Suppose I wanna minimize these mistakes. So Joe comes back with only a few books and I say, hey, you have a lot of false negatives because you didn't get all the stuff. It can't be just 3 books in there. I need a lot more stuff. So I'm increasing the retrieve set. And then I'm gonna get some of the missing ones, but I'm also gonna get more false positives. So if I decrease my retrieve set, I'm gonna minimize both FP and FN. Which means this is good to shrink it, but I'm gonna have more mistakes here. And then if I increase the retrieve set, I'm going to increase both of them, which means I'm going to have fewer of these, but more false positives. So we want to measure 2 things. We're going to call precision rate at retrieving relevant items. This is the true positives divided by the number retrieved. So who's retrieved? True positives plus who? Who else is retrieved?
False positive.
Hmm?
False positive.
False positive. So it's the true positives. This is the rate at saying if Joe returned to me 100 documents and 80 of them were good, the rate of good stuff was 80 out of 100. But that doesn't say anything about how many documents Joe missed. Maybe he did retrieve 100 documents or tapes or books or newspapers. 80 of them were good. So the rate was good, 80%. But Joe might miss 50,000 things, right? So he retrieved very few. They happen to be good, but he missed most of them. So the other notion that we need is recall, which is percentage good or correct information items collected. So that's TP divided by the relevant. So that's TP divided by TP is relevant plus who else is relevant? Fn. So to do these measurements, I need three numbers. I don't need the true negatives actually. True negatives is a sea of things that are bad and I don't retrieve them anyway. If somebody returns back a set of items to me, again, this could be web documents, books, items to buy, clothes, places to go, whatever, it doesn't matter. Precision is how many of those things retrieved are good. So at what rate if I follow what Joe did, I am successful. And recall is how many things you've got out of how many were in the warehouse. If you miss 50,000, even if you retrieve few that are good, you miss most of them. So in this example that I'm giving you, Joe comes back with 100 things. Most of them are relevant. His precision is close to 100%. His recall is close to 0. So that's an example of high precision, low recall, right? Those numbers are between 0 and 1, and 0 and 1. In the perfect case here, if this happens, what happens to the precision and recall in this case? Both are 100%. That's why it's perfect. You retrieve all good information and nothing extra. Now, how do I get Joe to retrieve a high recall but low precision? So the first example was the 50,000 good items, but he only comes back with 100 of them. They happen to be almost all of them good, but the point is he missed 49.9 thousand items. Now suppose that Joe comes back and says, aha, you want high recall, I'm going to give you high recall. What Joe has to do then?
Most of them he retrieves relevant, but a lot more of that is not relevant also.
Into extreme. In extreme, what Joe has to do to increase his recall?
Get every document possible.
Get everything. Then recall will be 100%, because the relevant will be all relevant and the TP will be all relevant. However, if Joe retrieves everything, what happens to the precision? The true relevant are 50,000, but the number of documents in the records in my database is 10 million. So now he retrieved 10 million things, but only 50,000 relevant, right? So that means his rate is like 0.22% precision. So if we want to increase precision, we decrease the size retrieved. And we stay with very good, very safe items, but we miss a lot of the information. If we want to increase recall, we increase the size of the retrieved document. So we retrieve a lot. And we're going to increase the recall, but we're going to collect a lot of junk in that set too. Okay? So now, I want to take these metrics and use them on a ranking. The problem in ranking is I don't have a set. I don't have a retrieve set, right? Google, theoretically at least, ranks all the documents from the web. Of course, no one ever clicked enough pages to see more than, say, 2, 3, 4, 5 pages. But theoretically, at least, when Google presents you a list of results, they mean to say, it's all of them. So assuming this list goes all the way to the billions of documents, how can I get some sets of retrieved? And I guess everything that's not in the retrieve set, we can call it not retrieved. What do I have to do with this list to obtain a retrieve set? So Google gives me a list, but I want really a retrieve set. I don't want a list. Actually, the web paginations offer you immediately a transformation from a list to a set. I break it, say after the first page, and I say the retrieve set is what? The first 10, and the not retrieve set is everything else. So that's called a cutoff. Let's call it a cutoff here. Cut off. The rank at which it's cut off is the rank on top of the line. Cut off rank 5. And now that I have this set of retrieved and this set of not retrieved, I can measure precision and recall, right? What will be my precision? I'm going to call it precision at 5 because I cut it at rank 5. What will be my precision? What's the set of true positives by rank 5 divide of the set of all good documents? And what's the recall at 5? It's also 3 by 5? How about I write it here? So recall at 5, it's 3 by 5. But what happens if I cut it at rank 7? So if I want precision at 7, what is that? 4. 4 by 7, right? Because precision is how many were good? 1, 2, 3, 4 by this rank, out of how many I retrieved? 7. And the recall at 7 is what? 4 by 5. Because 5, it has to do with how many relevant documents were total in there, right? Recall is divided by how many things are relevant. That's fixed. So in recall, this number will never change, this 5. This 5 is how many relevant documents were to start with. It's a fixed thing. Doesn't matter who retrieves it. There's only 5 documents in there to be retrieved to start with, correct? In precision, the denominator, this 7 or the 5, will always be the cutoff rank, right? Because the number of retrieved is where I cut the least. Okay? So I can do another thing that, so those are two notions, right? Precision and recall, and really you want to report both because reporting just one of them is misleading. Like I said, it's relatively easy to get high precision by sacrificing recall. You retrieve only one document which seems the most relevant. And it's also relatively easy to increase the recall by sacrificing the precision. You just retrieve everything and you just increase the recall. So what if I want to combine them into one number? Combine precision recall into one value. I want an average or some sort, but I want an average that's sensitive to low values. Say the arithmetic average, you can still get a good decent value by having one very high and the other one kind of low, right? So if I have a precision 100% and the recall 20%, my arithmetic average is 60%, not bad. I instead want an average that's sensitive to the smallest one. So as soon as one of them is small, the average goes down. So which average should that be? Harmonic average? Is sensitive to small values. So harmonic average is what? 2 precision times recall.
Precision plus.
precision plus recall. I think that's equivalent to say 2 divided by, is it 1 over P plus 1 over R, something like that? I think it's true, right?
Yes.
This has a name, this whole metric here. F1. This is the F1 value. 1 has to do the weighting. That's same as F. If you say F, you mean F1, means the 2 are weighted equally. When you say F something, it means one of them has more weight. Because it's like an average, but you can weight recall 75%, precision 25%. In fact, you can weight everything. You can combine this way with the harmonic value, any two metrics you want, but F1 is specifically precision recall into one value. Because it's sensitive to small values, if you get a high F, like 90% or 80%, you have to have high precision, high recall. Even at 70%, which with a normal average, arithmetic average, you can get 70% like 140, 101, 40 the other. In F, you can't drop too much one of them. If you drop one of them, the whole F value drops. F is used in a lot of data scientists. So like machine learning, data mining, a lot of them use F. And almost all sets measurements are done with F. So every time you retrieve a set of labels, and you may be retrieving 5 out of 6 correct, something like that, you know. Typically that's F value. Okay? So I have F. And I can define those sets by truncating the list. So I'm saying I can do these measurements at every cutoff here, right? So if somebody asks, for example, precision at 1, what does that mean in English? What are the options for precision at rank 1? What are the possible options? If the top item in my list is relevant, it's going to be 1, and if the top item in my list is not relevant, it's going to be 0. So precision at 1 has to do with I'm feeling lucky type of thing. Is the first item in the list good or not? Right. What is precision at 10? That's typical for web search. Out of the 10 results on the first page, how many of them are good? Right. Now, I want a metric for a list, a rank list, not for a set. So suppose I have a rank list of documents written by Google, 100. I'm putting the top first 10 pages together. So for a rank list, maybe before we do that, let's talk just a little bit more about how precision at rank and recall at rank and F work together. Let's do that first. Here's what I'm going to do. Actually, I want to show you two things that are related in concept, but I'm going to need two boards here. Somebody with salaries here. So what I want to show it is this parametric sort of plots. I want to compare let's say I have recall here, and I have precision here. I'm going to assume that if I retrieve only one item, I'm going to be with a very high precision and very low recall. So when the recall is very low, precision is going to be very high. But then if I retrieve everything, I get a high recall, This is 1 max. This is 1. And I'm getting a low, very low precision. So I'm assuming plots are rather this way. I don't know, I draw something at random here. So precision, what's hidden here, why it's called a parametric plot, is because the way I'm producing this plot is actually I'm going by the ranks in my list. The ranks are hidden in there. So suppose I want to do this plot. I'm going to erase that one and try to do this one. How do I produce a plot like that? The hidden here, param, is the rank cutoff. So what happens at cutoff 1? Recall it's at rank. Recall is what at first rank. So what's recall at 1? So precision at 1 here is 1, and recall at 1 is what? 1 by 5. So if I have to put those numbers in the plot, I get 1 by 5, right? And that is 1. What I'm going to do on this point is k equal, what was my cutoff? It's not really an axis, the cutoff, but this is k equal 1, right? What happens at k equal 2? Recall would be 2/5, and the precision is 1. So k equal 2 is right here, the cutoff. What happens at k equal 3? Precision is still 1. What happened at k equal 4? Recall stays what it was, because recall, to increase recall, I need to get the relevant document. So recall is still 3 by 5, and precision dropped. Now precision is?
3, 4.
Which is? So where is that plot? That's in here, right? This is 3 out of 4. So this is k equal 4. So the recall stayed the same, but the precision dropped. What happens at the next rank? 5. Recall will stay the same, and this precision will become?
3 by 5.
Which is?
0.6.
Where is 0.6? This is 0.5, right? Here somewhere? So this is k equal 5. What happens at rank equals 6?
Precision is
Recall
recall is
increases. When recall increases, it increases by how much? Always by 1/5. Because if there's 5 relevant documents, if I get one of them, I'm increasing the recall by 1/5. So recall will go here, and recall will never drop. Once it reaches this line, if the precision will play on that line until I see the next relevant document when I'm moving to the next recall, right? So what happens here? What is the precision here?
4 by 6.
So where is 4 by 6? Compared to this 60%,
2 by 4.
where is 4 by 6?
2 by 66.
It's here, right? 4 by 6, somewhere in there. So where is this going to be? Here? K equals 6. What happens to k equals 7?
4 by 7 precision and
Recall stays the same, right? Because I got a non-relevant document. And the precision will be 4 by 7. Where is 4 by 7 compared to, say, 60%?
0.5.
It's lower? It's somewhere in here?
Yeah.
And let's do one more. At 8, I got a recall of 1, because I got all the documents right in there. And then precision became,
5 by 8.
how much is 5 by 8?
0.6.
0.6 something. It's maybe more than 0.6 but below 2/3.
Yeah.
So you're gonna see this plot, but not the case. I put the case, I wrote them down, but what you see in a precision recall plot is this, going down, right? And here what happens here? It actually goes up, right? Because when I see a relevant document, clearly the recall increases, but the precision goes up a little bit too. And then down, and then up, right? So this is what you end up seeing. Let me make it more clear. You see this. As a precision recall plot. I put a case to help out the visualization here. It's a hidden parameter that typically you don't see. Because you only see recall values and precision values, but you don't see explicitly which rank they've been calculated. So in particular, say recall 1, once I hit this 8, everything after that will be on this line, right? Because I hit all the documents now, precision just gonna decrease. If I keep going, I'm gonna see no relevant documents, I'm gonna decrease the precision, but recall is gonna be a 1. So the other plot I wanna show you is the plot that has to do with true positives versus false negatives versus, so these 3 numbers here. So let's see how we do that. You guys can tell me the name. This is a very famous name for this plot. So it's false positives versus true positives. Everybody knows the name of this plot? How it's called? No? Okay. Maybe it comes to us as we move along. So, but what's the, more importantly, the way I'm showing you these 2 plots now one after the other, there's a hidden, what? Hidden parameter, which is the rank. Okay. So imagine I have a rank list of results. If I stay at the very high levels, I expect to see the relevant documents, right? Even a bad search engine, the top few results are the obvious relevant ones, right? If I type right now, you know, Northeastern University, even if my search engine is not very good, the few documents are gonna be like the Northeastern University page and all that, right? Agree? So let's assume the top has more relevant documents, and as we go down, good retrieval system will keep the relevance at the top, and bad retrieval system will start producing quicker non-relevant documents and have the rest of relevance down, right? Let's assume that. So at high K, what is gonna be TP and FP? So if I only look at the first document in my list, which is high and which is low?
TP is high, FP is low.
TP is high if I only look at one document. So let's take this example, Northeastern University. How many documents are about Northeastern University on the web?
Are you doing a rock curve?
Yes.
Okay.
ROC curve stands for what?
Receiver operating characteristic.
Very good.
Which I don't know what that
We
means.
will heard of that for sure.
What's that?
ROC curve? Okay, doesn't matter. ROC curve, something again, you go to the interview. They don't know what ROC stands for, but you have to know what it is. If you don't remember, I don't remember what ROC stands for, it's fine. But if you don't know what the curve actually is, false positive rate versus true positive rate, that's a problem. I think it's actually rate, FP rate, TP rate. We'll see in a moment what rate means. The point is, when I retrieve very few documents, low k, so this is k equal 1, I have a very small false positive rate. I didn't make mistakes, but I also didn't retrieve many good documents. So as I move along, I'll have increased the true positives and increased the false positives. When I move along with higher k, so this is k equals 0, maybe I have another one that's k equal, I'm going to say k equal 5, and then k equal 10, and then k equal 30, and then k equal 50, and then k equal 100. I can join them. Something like this. So what do we want for a system to be good? All the system, when they retrieve all the documents, let's say at the limit here, this is k equal all. I retrieve all documents. What's going to be the true positive rate? We'll call it 1 at that point, and the false positive rate, maybe it will be 1 or max. That's when I retrieve everything. All systems, retrieval systems, when they retrieve everything, will end up in this point. The difference is how they behave in the middle. What do the good systems do? So how do we want the rates to, which one do we want to increase faster to be good? The more we go this way first, is better. If we increase the true positives without false positives, it's good. If we increase this way, like we're getting a lot of false positives without retrieving actual true positives, that is bad. So a random system will go flat. This is random. This is the, remember when people came with 0.002 language model? That's this line. I sort them at random, and that's my list. If a system is here, that is very good. In fact, this will be excellent. Retrieve all the true positives without any false negatives. By the time I got the first false negative, I already retrieved all the positives. And if a system is here, this is very bad, because this system retrieves, this is incorrect, because remember, all systems have to go in there. All systems have to get to that point, so here's a system that's very bad. This system, or search engine, retrieves a lot of false positives before it actually sees the correct ones. So this is a parametric plot, because every one of these points corresponds to some sort of cutoff in the list. But the cutoff is implicit. You don't see the case, you just see the plot. False positive rate, true positive rate. This system starts at the top of the list, and on top of the list you always here. Because you have no false positive, no false negative, no true positive, no false positive. At the end of the list, when you look at all 6 billion documents, you always here, you got all of them. The question is, what was the rate? Did you increase true positive rate without increasing much false positive? Or you go, this is random. Random means if my true positive overall rate is, say, 1 in 20 documents, by randomly sort the documents, I'll have increase, the rate will be 1 each 20, right? For every 20 documents that I get, 1 will be positive, so this will be a flat line. But the good search engine might actually find the true positives much faster without getting bad ones. While a bad system will get the false positives before getting the correct ones. So now what about this rate? What is a rate? So can we get the rate here? I think this is something to do with those let's see. True positive rate. I think let's get these things right. True positive rate, I think, is the same as recall. Is that true? Is that recall? So we think this is TP divided by TP plus Fn. And false positive rate is Fp false positive by Fp plus Tn. So which one is that? Fp plus Tn. The problem with that definition so that's correct as mathematically speaking. In IR, you got to be very careful about this TN thing. In machine learning, you have classifications, right? So you have things like documents about politics versus sports. Classes are more or less balanced. So you talk about true negatives with respect to sports, those are the ones that are not sports and not predicted as sports. So these numbers make sense. In IR, true negatives, it's something you want to avoid at all costs. Why?
It's too much.
Is huge compared to everybody else, right? So suppose I have a query about anything, Northeastern University, nuclear bombs, shipwrecks, whatever. If you look at how many documents are on the web, or even in your crawl, but are really not retrieved, that's going to be 99% of them, a huge number.
This is a question that's related to data mining and it's related to IR. It's kind of in the middle. And the question is, a lot of times you see imbalanced classes, like you were saying, with like a lot of false negatives, for example. And
True negatives.
Yeah, true.
Typically, the true negative is a big number because it's the ones that you don't predict and they're not supposed to be predicted, and 99% of the data fits in that category.
Yeah. So with the data mining, you undersample or whatever to get the classes more balanced out, and then do that. But the models start to get kind of wonky, and so I'm wondering where if you have a feel for where the line is between like, oh, my classes are really imbalanced, let me try some more IR stuff, or.
So I can look up an exact answer for the question, but here's what I know right now. If it's reasonably unbalanced, as in 10% versus 90%, you can still do sampling, right? In most cases, depends on the data set. If you sample them appropriately, you can correct for that bias or do things like bagging algorithms, right? When you duplicate some data for training purposes, you consider each training of the skewer class, kind of give it an importance if you want, and you consider it as 2 points. So you can do that if it's off balance, but within the same scale, like, say 10%, 90%. In IR, you cannot, right? There's no way to take, a query might have 20 relevant documents and 6 billion non-relevant documents. That's way too imbalanced to use anything like this. So that's the reason when you measure IR, typical accuracy doesn't work, right? Accuracy in machine learning sense, you get a point when you're right and lose a point or to get any point when you're wrong. You would get a high accuracy by saying no relevant to everything, right? If you just measure accuracy that way, you will be 99.99% accurate for just saying no all the time. It doesn't work for IR, but it still works in machine learning, typically with some sampling or balancing or importance factors, perhaps. That's how polls are conducted, right? When people do election polling, they take into account the correction factors to correct for the bias between the classes. So even though I know Boston is a highly democratic environment, I can still accurately estimate how many people will vote Republican for Republican governor or things like that. So polls get very exact by doing this correction, as an example. I think your question is, okay, what do we do in IR? The actual question is, at what point do you decide that sampling doesn't work? For that, I don't have an answer right now. But in IR, we have to use a ranking measure. And that's actually be done even in machine learning when you're looking for one or two things out of a million sometimes. If you were to have that kind of data experiment, you want to use a ranking measure, because ranking, even if it's one or two in a million, will correctly show you that you've got like average precision, the measure that you guys see in Trek Eval there. Even if you have 3 relevant documents in, how many were in AP89? 85,000? Even if it's only 3 out of 85,000, average precision will only go high if those 3 are on the top of the list. Now, we didn't talk yet about average precision. That's coming next. But the ranking measure have no problem with bias, no matter how skewed it is. So, because of that, now it's pretty much done. There's a large development of machine learning algorithms that have the objective ranking measures. So things like lambda rank, for example, used by Microsoft in their search engine and other projects. What else? Some of the JForest code. So there are machine learning algorithms, not the typical ones like regression and boosting and neural networks. You have to study that as a separate class of algorithms. That internal objective is ranking. So they have no problem with this kind of bias between the labels because they don't optimize for accuracy. Okay? It's a little difficult to optimize for ranking. It's not, when this came along, I think 2005, they were the first breakthroughs into how to do machine learning for ranking. This was a big deal because not obvious at all. The measures were known for many years. These measures, precision, recall, average precision, they're known for maybe still at least 1990. So we're talking about 30 years or so. But the big breakthrough into learning to rank as opposed to learning to optimize accuracy, that came along about 2005, 2008, I believe, about 10 years ago. There's another question?
Wouldn't F1 value would be, it would be immune to the unbalanced classes? Like F1 would be a good measure to...
Let's see. So he's saying, can F1 has the property of, not the accuracy problem that you can get a high accuracy, you're just saying no to everything. Is that true or false? So can I increase F1? Can I show up with a high F1 without having good precision and recall? Both of them. Can I have a low precision or low recall and still have a high F1? I look at the formula. Times precision times recall divided by this. If one of them is relatively low, the whole F goes low. So that's true. But how to optimize F1 in a machine learning algorithm is still a difficult problem. In fact, that's a current area of research for problems that have multiple labels. So you don't just have to predict one thing like a category, but you have to predict multiple tags. The typical evaluation is F1 for those tags. So how to optimize for F1? As far as I know, people came up with a wrapper on top of machine learning algorithms to do so correctly. So there's another thing. I think F1 works well when you have two classes. But what if I have an imbalance between 6 classes? What do I do then? Right, I mean, that's,
I think because I had a project last semester and the classes were like hugely imbalanced and we had a multi-class classification problem.
multi-class or multi-label?
Multi-class,
Right.
multi-label, yeah.
Multi-label, you can be more than one.
Yeah, I mean,
Yeah. So that's difficult. Multi-label problems where some of the classes are very rare are known to be a current open problem. I can give you, we study that, a part of our lab has few students that do that exact research for their PhD. Multi-label classification with dependent labels, because the problem is really dependency between the labels. If labels independent, you can just predict each one of them separately. With dependent labels, where some of them are very rare. So there's a large body of literature last few years that people have tried. Things like CRF and PD-sparse and algorithms specifically designed for that kind of problem. In my medical data, we have that because some of these diagnosis codes that doctors use are extremely rare. So, you know, codes like coughing and, you know, headaches and stuff that happens all the time are very popular. Things like radiology codes and x-rays and, you know, that happens routinely. But there are some codes that are extremely rare and hard to predict. Okay. So I wanted to show you two plots that are parametric in the ranking effectively. Every single dot on these plots is obtained by a cutoff at some rank. But the cutoff is implicit. You don't actually see the cutoff unless you label the plot like me, k equal 4, k equal 5. You see this plot, but you cannot be sure. If you don't see k equal 5, can you be sure this is k equal 5? In other words, if I tell you I've got at recall 60%, I've got precision something, can you determine from that information alone which is the cutoff? If I only give you the point, I give you the coordinates. This is the recall, and that's the precision. Can you say for sure this was cutoff equal k equals 6? I mean, you don't see the list. If you see the list, you can maybe, I don't know. But if you don't see the list, can you? No. So that's why this case, if you don't label them on a plot, they're implicit. You can determine the exact k just from the two axes. So now, how do we take the precision recall and make a measurement for the list? So in here, if you, I don't know if you remember the ROC, I think he was saying he remembers that. There is a measure associated with ROC curves, the quality of an ROC curve. Because here's what we want. We want to go first up.
Are you talking about the area under a curve, the R
Right.
curve or something?
So the AUC is area under the curve is quality. Because the higher the curve goes initially, the higher the area here, the lower, you can see this has a lower AUC, much lower than the random, much lower than this. And in here, you're gonna have an exercise for Wednesday. I'm gonna give you a metric, average precision, and I'm gonna say, is the average precision roughly the area under this curve or not? So what is average precision? Now I'm going back to the rank list here. Average precision is the average of precision at k where K is relevant rank. So in other words, I want to average the precision values, but not at all ranks. But which ranks in this example? So average of what ranks I'm going to consider there. So I'm saying take the precision at K, these numbers we have here, but not 1, 2, 3, 4, 5, 6 up to 10, just some of them. Which ones? At rank 1, I get 1 out of 1. At rank 2, I get 2 out of 2. This is the precision values, remember? At rank 3, I get 3 out of 3. What other rank I need to put here? 4? No. I'm only doing the relevant ranks. So I do 6. Precision at 6 is? Precision, what's the next one?
8.
8? 5 over 8. So if I average these numbers, how do I average these numbers? I get 1 plus 1 plus 1 plus 4 sixths plus 5 eighths divided by how many? 5. This is arithmetic average. It's the precision values at relevant ranks. So what happens if I don't see all the relevant documents? I show here the top 10. In the homework 1, you guys did how many? 1,000. Right?
Yeah.
What happens with the relevant ranks? Did we really, can you promise for sure in that 1,000 documents, did you include all the relevant ranks? So suppose a query 93, has 48 relevant documents. You listed 1,000, right? How many relevant you included there? Maybe you included 42 relevant documents. So how many relevant ranks you're gonna have? 42 in your list. But the truth is, there's actually 48 relevant ranks because there's gotta be 48 relevant documents. If you list all the documents in collection, all 85,000, you would have some of these 6 ranks that you're missing are over the rank 1,000. So that is a alert for you guys. Very common mistake in computing average precision. Very, very common mistake. Here's the common mistake. I have a list, L, N, L, R, N, R. This is the display cutoff. In your case was 1,000. Right? Say BM25, you carry out 1,000. But in reality, you would have other documents here, N, R, N, R, right? Some other ones that you didn't display. If you were to rank all 85,000, you would get those ones too, but because you cut off your list, you only have here. The mistake people do is to compute this number as it is for the display. So this is a mistake. To say average precision in this case will be what? 1 out of 1 plus, this one doesn't count nothing, this is 2 out of 3 plus 3 out of 4 plus 4 out of 6 divided by 4. Clearly a mistake. Because it doesn't account for all relevant ranks. It only accounts for the ones you see. If this would be the way to do it, I can increase average precision very easily. How? Chop off the list here, and I get 1 out of 1, declare it good, right? So you can't just average what you see because you decided to truncate at 1,000 or 6 or 7 or 100. You have to include all the relevant ranks. But people do an approximation because they don't want to retrieve more than 1,000 or 2,000 documents. They don't know where those relevant ranks are. They know they mix a few. So my example, I said you retrieve 42 in the first 1,000, you miss how many? If there are 48. You miss 6 of them. in this example here, my display misses how many relevant documents? 3. I missed those 3. So what people do to compute average precision, they say, I know I missed 3 documents, but I don't know at what ranks those documents would be if I would really rank the whole list. So how can I do this correct? It's not us. So correct. The problem is I don't have the precision values here because I didn't even go that far. I don't know what I know I missed 3 documents, but I don't know at what ranks they would appear. So here's what I'm going to do. I'm going to average precision. I'm going to say it's 1 out of 1, plus 2 out of 3, plus 3 out of 4, plus 4 out of 6. That's the ones I see. The remaining ones I don't see, I'm going to say they're 0. And then I'm going to divide by how many? 7. 7. So what's the difference really now, mechanically speaking, between this and this?
You reduce.
The numerator is the same because all this does add 3 zeros. So that's not a problem. The problem is instead of dividing with how many documents I see in my display relevant for, I have to divide with all the relevant documents in the collection. So how does Track Eval does this correctly? If you only display 1,000 things, and in there you include 4 relevant documents, how does Track Eval, the program, knows to divide with 7, not with 4? How?
You provide it for
The curl file. The curl file has all the relevant documents in it, whether you retrieve them or not. So Track Eval goes in that file and he knows you've seen those 4 and you missed 3, and then he knows there's 7 total, so he divides by 7. You can think of this, if it's easier, into each relevant document has a value associated to it, precision value, 1, 3, 3. Those are zeros because I don't retrieve them at all, they're not in my display. And I divide by how many relevant documents are, which makes sense by definition, right? Do we have the definition somewhere here? Maybe not. At relevant rank. So I know from the beginning how much I have to divide with. If there's 25 relevant documents, this is going to be division by 25. And I'm going to have 25 precision values. If some of those I don't actually see, I'm going to count those precision values as zeros. So that's average precision. And if you see the term mean average precision, or MAP, is the mean of average precision over a set of queries. So I compute average precision per query. Track Eval does that if you put a minus Q sign in there. And then it gives you an average for all 25 queries. That's called the MAP. It's a little bit, I don't know, funny language because mean and average mean the same thing, right? Mean, average, precision. Well, why is not average, mean, precision? Like, it means the same. But that's the name, people got it, mean, average, precision. Mean is over queries. Average is for each query now. Average is over the relevant documents. Okay. So there is something for historical purposes that is completely useless today, but just in case you hear that term, I want you to know what it is. You're going to hear the term interpolated plots, precision recall plot. This is called a precision recall plot. The homework might ask you to compute a few of those to print them out. So people have thought, we don't like the fact that this curve is going up. Doesn't feel good to us because precision recall is not supposed to go up. The truth is, it actually goes up. Every time you see a relevant document, definitely goes that way, but it has to go up a little bit, right? So people have said precision recall curves are supposed to go down. We don't like that they go up like that. So how do we interpolate them to make them not going up? So somebody long time ago came up with an idea, say, hey, take this peak and instead of going down and up, we go flat in here. We never go down more than the point on the right hand. So the actual interpolated plot goes to here, then goes like this, and goes to here, goes like this, never actually goes up. It goes only down, flat. Nobody uses that anymore, it's antique. Like, no information retrieval, topic or project or exam will have that. But if you ever hear the name interpolated plots, it means hack them up so they don't go up, they only go flat and down. Okay, so I think that's what we have for the first evaluation part. And I think that's most of what you need no, you need something else for homework 5. We're gonna do that next time. That is, average precision works with binary judgments. Everything I showed you today, it's relevant, non-relevant, yes or no. Now for your homework, you're gonna have 0, 1, 2. So not too easy to compute something like average precision when you have a 3-grade thing. For that, we're gonna use NDCG, this other measure. But we can take 0, 1, 2 and make them binary first and then compute average precision, right? If we really want to. We can establish a convention which is either 2 stands for relevant, 0, 1 means non-relevant. Or if you're lenient, you can say 0 stands for non-relevant and 1 and 2 stands for relevant. So you have more relevant elements either way. Then if you make it binary, you can compute these values. The last thing I'm going to say today is also for historical purposes. Nobody uses that. It's something called R precision. That is, assuming I know R, number of relevant dogs, which is necessary for this metric, like average precision. Again, this in here, this is actual R value, like how many number of relevant. This is very simple. It's the precision at rank R. So for our example, how many relevant documents we have? We assume these are all the relevants, like we didn't miss anything. How many relevants are here? 5. So that will be precision at 5. The truth is, precision at R happens to be the same with the recall at R. Why is that? Precision at R is the TP at R divided by R, right? Because it's how many relevants you see by that rank divided by the rank. Who's the recall at R? They have the same numerator, it's TP at R. Recall is always divided by number of relevant documents, R. So you see how they are the same? So the reason this is of interest is that this is the point in the plot where this curve intersects the main diagonal. This here is R precision, where precision and recall are roughly the same. So it's useful because you have this balance between precision and recall. You can increase precision, decreasing recall, or you can increase recall by decreasing precision. But you can't play with R precision. If R precision value is high, both of them have to be high. And if this is 1, it's got to be a perfect retrieval. The only way to get an R precision of 1 is if all your top R documents are the relevant ones, and after that, nothing is relevant. What's the difficulty here is that this is hard to approximate if you don't know R. I mean, average precision is easier to approximate, but still suffers of the problem of you have to know R. So next time, NDCG and something about user status. But like I said, my worry right now is that this is already too advanced for where the homeworks are, right? You guys need to do 4 first, and then this. Are we happy with the TA hours? Good? No problems? I'm asking them to do the homeworks in advance a little bit so they have the answers for you. But that doesn't happen all the time.